Project part 2. So this is posted on Canvas as of, I think, Wednesday. As of yesterday, I posted, I think, 4 kind of numbers or sort of like little bits of information of which of the flow streams to use. So we're all going to be starting off with the same basis flow rate. So use those ones. If yours are very, very close, then you can just use yours. Right? For all the project grading, I'm okay within a plus or minus range. That's pretty generous. So if yours are close to the ones that I have, you can go with those if you'd like as well. So it shouldn't impact the numbers too substantially. So I have this as listed as due on Tuesday. I think it's very possible to get it done by Tuesday. I chose that because that's the last official day of classes. Wednesday's reading day. So if you need more time, just let me know and I can push it back. I just didn't want to go too far into the finals period. So deadlines suck, but deadlines are also kind of nice in order to force us to do activities. So if you want more time, let me know. Basically, you can have more time on this if you want it. But we'll keep this here for now. All right, but the good news is that many of you on the exam did very well on the reaction balance problems. Right? I think the algorithm is understandable. Choose heat of formation. You know, the enthalpies are just heat of formation plus, integrating C sub P dt. The good news is that you can do that for most all of these problems. So if you build one really good spreadsheet, then all you basically have to do is just copy in the inlet streams, their inlet temperatures, the outlet streams, their outlet temperatures, and then you got Q, right? So they should go relatively straightforward. What I am a little concerned about is problem number 3 on this most recent exam. One that did not involve a reaction, but by which many individuals attempted to solve it using the same algorithm with a reaction. And you know what? That is actually totally acceptable. I believe some people got it by synthesizing methanol from nothing, synthesizing ethanol from nothing, and then manipulating the enthalpy values. But what I saw happening when I was grading that problem, which was a doozy to grade, is that you would switch references partway through, right? So you would start off with like the heat of formation, but then when it got to going from like to the liquid or the vapor phase, right, you would have like negative 200 in this, negative 200 in this, and then you'd have positive 50 of this, right? So you would just like slap in the heat of vaporization, right, where it should have been the delta H of formation, then the heating, then the heat of formation. Another really, really common thing that I saw was I asked specifically, and this is, you could have solved it without this information. I was trying to guide you in a way that I thought was easy to solve this problem. What was the heat of formation of the 2 components at 65 degrees C? So methanol was basically already at 65, so that one was more or less just the table value of the heat of vaporization. What I found, though, is that the most common mistake is that people got that you sort of heated the liquid, vaporized it, and then cooled the liquid. But the temperature that you heat it to or cool it to was the issue. Everyone did, not everyone, a lot of people did 25 to 65, right? Or because that's 25 is sort of the standard state. What we needed to do, right, was to go from the outlet conditions of 60 to the boiling point, right? That's how you get the heat of vaporization at that particular point, right? So, or rather you go from the normal boiling point to 65 and then integrate it back. So I still think, so many of you got the reference states down pretty nicely. I think when the reference state is forced upon you, in the case of the reacting system, everyone feels very comfortable with it, or most people feel pretty comfortable with it, right? But when the reference state is a user selection, that's where I see that there's some complications getting thrown in. So maybe something to brush up on is when you're having a non-reacting system, you get to choose a convenient reference state. The only reason why the reference state is fixed for a reacting system is because we don't have data except for what is the energy released or consumed in a reaction at 25 degrees C. So go back, and if you got number 3 wrong, please take a look at reference states again and brush up how to calculate heats of vaporization at arbitrary positions. Because the concepts are the same as in the heat of reaction. So I know you all can do the physical work of it, but I just want to make sure that everyone leaves this class with the conceptual understanding of choosing a pathway through thermodynamic data starting at a reference point. Okay? But for the most part, a lot of people did very well on the exam, okay, which is good. Okay, so this is going to be my run-through as the guide. Hopefully this video is preserved and the audio is acceptable, so you can use this as you're working through the project. So I'm going to go through each of the problems one by one, explain the calculations, explain the purpose behind this. Okay, so first one here, these are all about the steam reforming reaction. So what is the rate of heat transfer into the steam reformer, right? So this is not the combustion side. The second part of the question is, how much methane do you need to burn to provide this amount of heat? Okay, so let me go to the process flow diagram to the steam reforming reaction. Okay, so we have the steam, right, that comes in, mixes with the natural gas. It is going to be heated up to 450 degrees C. This is your inlet condition for the steam reforming reaction. It is going to react, and then it is going to come out at 855 degrees C. So that is the condition. So you need to figure out what is the inlet composition here, which is methane and steam, right? 1600 and the 4800. And the outlet composition, this is going to be something that I provide to you in that help sheet, right? So you just need to figure out, you're going to heat the reactants and products, and you're going to perform the reaction, which is going to have some delta H of reaction. So you could either use a delta H of reaction approach, in which case you would need to account for the steam reforming reaction and the water gas shift reaction, or you can use the heat of formation approach, and you don't care what happens in the reactor, right? All you know is what goes in and what goes out. The second part of the question then is talking about this other stream where we are combusting the fuel that is at 30 degrees C and 1.6 megapascals, and then it is going to mix with the air here that is at 300 degrees C and 5% excess. I'm not providing this information in the help sheet, but this is, I think, question 3 on project part 1, but it's just a combustion balance with 5% excess air and a little bit of water. The combustion gases are leaving at 960. So what you need to do in this problem is you can choose a basis of 1 kilomole per hour of methane, figure out what the Q is, coming in at 30 for the natural gas, at 300 for the air, and both the flue gas and everything leaving at 960. What is the Q released by this process per kilomole? And then you scale such that the energy gained by the reactor is balanced by the energy provided from the methane, rescale the basis, figure out how much methane you need to burn in order to achieve that number. Make sense? Alternatively, if you wanted to, you could actually solve this in one go, right? You could do a balance on the whole process where you have 1, 2, 3, 4, 5 streams coming in, all at different temperatures, all at different flow rates, right? You could solve that in one go, but I'm having you break it up into 2 parts. But if you really wanted to, you could solve it in one go, just making sure that's adiabatic, right? Set for Q equals 0, and then change the flow rate of the natural gas, which of course would mean if you change the natural gas flow rate, you're going to change the air flow rate. Does that all make sense? So you don't have to break this into multiple steps. I'm just having you break it into multiple steps to make the balance a little bit easier. Okay, so that's question 1. Question 2 is a little bit of a tricky one. So this is the energy integration. So what we're asking for here in question 2, and I raised it up really high. Okay. What is the rate of steam generation by cooling down the burner effluent, right? And there's some notes here that you're going to have to balance some other streams. And then what is the rate of steam generation by cooling the steam reforming reactor effluent? So let's go back to the process flow diagram. So if we look at the burner flue gas, we have 1, 2, 3 heat exchangers. The first one is used to preheat the steam and methane mixture to save some energy to get it to 450. So if we did not do this energy integration, it would require much more methane combustion because you would be mixing stuff that's a significantly lower temperature. So before you even get it to the reactor conditions, you would have to spend a lot of energy to heat it up in the first place. So one stream here preheats this mixture. The next stream generates the boiler water. This is the number I'm asking you to solve for. The final stream preheats the air to get it to 300 degrees C. So in order to determine how much steam you are generating in this process, you need to balance 1, 2, 3 different processes. So you can do this either determining how much energy it takes here and then figure out what the temperature is in the middle, then figuring out how much energy is generated here, working backwards, figuring out the temperature in the middle, and then balancing this one here. So you can either go 1, 2, 3, or you can do one big balance. Those are both equivalent processes. Okay? So you can figure this out by doing one big balance or 1, 2, 3. So that's what's asked there. The second part of this question is this step right here. So we have 855 coming out. This is the syngas, the carbon monoxide hydrogen-rich mixture. This boiler water comes in at 30 degrees C and 4.8 megapascals, so steam tables, right? Leaves here 100 degrees superheated at 4.8. That's 100 degrees above the saturation temperature of the water at 4.8 megapascals. Use the steam tables here as well. Anything involving water, use the steam tables. Do not do C sub P delta T, because these pressures and these temperatures are going to be way, way, way more accurate by using the steam tables. So then this steam reforming reactor material gets cooled down to 15 degrees above the temperature of the superheated steam. Okay? So let me explain a little bit about heat exchangers. So when we talked about flame temperatures, we talked about the importance of not just the energy, but the temperature as well. The second law of thermodynamics says that as the temperature goes up, the entropy goes up. Okay? And what that means, if you work out all the fun math, is that temperature only flows from hot to cold. It doesn't go from cold to hot. If it goes from cold to hot, you violate the second law of thermodynamics. So that means if I need to transfer energy from the reactor effluent here to the steam, that means it has to be hotter. So when you design heat exchangers, you design them based on a certain temperature difference. That's why the design specification here says it's 15 degrees above the temperature of the superheated steam. This one is 100 degrees above the saturation temperature. Now this seems arbitrarily convoluted just to test your vocabulary, but in fact this is how we would design the actual plant. Right? The 100 degrees above superheated gives you a certain margin of energy before the water starts to condense out, and you have to deal with two-phase flow in your pipelines. The design of the heat exchanger dictates that you want to have a certain delta T. So if you want to cool this down by generating the steam, that limits that other temperature condition. And that's why these sort of process design specifications kind of spider web out. Does that all make sense? So it's not arbitrarily convoluted. This is actually as convoluted as chemical engineers discuss things, which is fun. Okay, number 3 is a little bit tricky as well, but it's not too bad. This one's talking about the condensers. It's asking you to determine basically what are the temperatures of and the rates of heat removal for each of the 3 condensers designed to remove water from the SSR product stream. Okay? So in this one here, we are now talking about these 3 condensers. So in the last part, you lumped all of these together, right? So you went from 35 degrees C to whatever this initial temperature was that you didn't have to worry about. Now you do have to worry about it. And you determined what is fully saturated water at the vapor pressure of water at 35 degrees C. And then from the material balance, you figured out how much water had to be removed. So now what you need to do is work backwards. Let's say we are removing 1/3 of the water in each of these different condensers. So what that requires you to do now is to do a material balance and then figure out at that mole fraction of water, what is the saturation temperature going to be, where you can use the steam tables or Anton's to figure that out. And then you have to balance each of these three condensers with a phase transition energy balance. So not a reactor balance on this particular one here. Okay? So the tricky part is first doing the material balances, calculating the mole fractions of water, and then working out what does the temperature have to be such that that mole fraction of water is the 100% saturated mole fraction of water. Okay? Question 4 seems very difficult. It's very long, but you can more or less use the same table to work them all out. So this one is all talking about the methanol synthesis reactor. Okay? So in part A, and so this gives you a little bit of description here, but essentially the reason why the methanol synthesis reactor has sort of some unique design characteristics is because they're trying to control the temperature within it. So they are stating that the catalyst that is being used will become deactivated at 250 degrees C. So what ends up happening in these high temperature reactors is that the catalysts are typically some sort of a metal alloy. So how a commercial heterogeneous catalyst works. Okay, so you have gas molecules that are all floating around and randomly bumping into one another. Right? Gas phases are typically relatively low density. What a catalyst does is it acts as a collection site for material to stick to the surface of a solid interface. Then the molecules will diffuse in a 2D dimension as opposed to a 3D dimension in the gas phase. That changes sort of the electronic properties of the absorbed material such that it may make it easier for them to react. And in addition, it concentrates them and constrains their diffusion to 2 dimensions, and it increases the number of interactions of the two types of particles with one another. So a good catalyst, right, you want the molecules to absorb to the catalyst surface, not too strongly so that they don't desorb, not too weakly so that they just pop right off, right, and then modify the electron cloud structure and behavior such that when two molecules bump into one another, it promotes the formation of the desired product. Then you want that product to also desorb off readily. So, one second, Miles. So how we accomplish this in sort of the design of a catalyst is we find different metals that have the characteristics of the adsorption and desorption, and then we alloy it with other metals that slightly shift those a little bit one way or the other. Hey, this metal's kind of good, but it doesn't absorb things strongly enough. Let's add in a different metal that is more electron donating or electron accepting, and that maybe will lower what we call the Fermi energy level. Right? So we design these catalysts to be of a certain crystal size, a certain crystal orientation with a certain metal alloy composition, and that finely tunes the adsorption strength and desorption strength. If you're interested in catalysis, a graduate degree in chemical engineering may be right for you. Okay, question.
What does it mean to desorb, like for the molecule initially to desorb off the catalyst metal?
So, bare surfaces are high energy surfaces, so that if any molecule sticks to it, it lowers the global system energy. So if that molecule sticks to the surface very, very strongly, it lowers the global system energy. The issue is that if you have a molecule that really, really likes a surface, then it'll never pop off again. So desorbing is due to sort of the random kinetic energy of the process. So the metal surface is vibrating with a certain temperature, the gas molecule is vibrating, and every once in a while there's enough energy and it goes, it pops right off, right? Because you have a Boltzmann distribution of velocities. So every once in a while you'll get a high velocity metal shooting up with a high velocity of the gas wanting to pop up, and then it'll desorb. So you want to match sort of the thermal energy of the system to the absorption energy of the system. So what happens is at these high temperatures, these really delicately constructed alloys, the metals can diffuse, right, and they'll phase separate. So what normally would have been like an aluminum oxide alloy or some sort of iron alloy, it'll just phase separate into pure iron and then whatever the extra material was. And then the catalysts don't work so good, and you have to replace it. And replacing catalysts is going to be on the order of millions and millions of dollars for a large commercial reactor, right? You do have to change them every once in a while because you get buildup of contaminants and byproducts. If you have sulfur in your methane gas stream, sulfur is a well-known catalyst poison for most materials. So that's why it's very important to sort of baby your catalyst, right? It's a very expensive workhorse in a chemical plant. So that's what all this description up here is. In this case here, you're going to be using a 45% conversion of carbon monoxide and a 30% conversion of the CO2 in order to do your material balance. Part A says that if the outlet is, no heat is removed and the reactants are fed at a temperature of 210, what is the outlet temperature? So this is an adiabatic reaction. Okay, you're not taking out any heat. If you don't take out heat, are you going to deactivate your catalyst, which deactivates in this problem statement at 250 degrees C, right? So if you don't take any heat out, what's your outlet temperature? Part B says, what is the rate of heat removal if you have the stuff leaving at 250 degrees C? So this is the same table that you can use for all your calculations, right? In one case, you do a goal seek to set Q equal to 0. In another case, you fix the temperature to 250 and see what the Q is, right? Does that make sense? So it's a lot of questions, but you can still do the same calculations. Okay. Part C is more or less the actual reactor design. So we'll go to the process flow chart in a moment, but what they do is that they feed 70% of the reactants at 130 degrees C, and then 30% enters at 210, right? So repeat your calculations in A, saying if I run this as an adiabatic reactor, but I feed some of the stuff at a lower temperature called a quench stream, right? So you inject the chemicals at different positions in order to cool down the reactants and hopefully not deactivate your catalyst, then what is your outlet condition going to be? Again, you can use the same sheet, but you just have to split your feed stream into 30% at one enthalpy, 70% at a different inlet enthalpy. Okay? Part D is you're going to repeat this process. It's going to be adiabatic, but you're also going to couple it with the reaction equilibrium. So now this is a three nonlinear simultaneous equation solving problem. Because if you change the extent of reaction of the methanol synthesis reaction, if you change the extent of reaction of the water gas shift reaction, you change the temperature. If you change the temperature, you change the equilibrium constants. So you have to solve all three of those unknowns simultaneously. But thankfully, computers are really good. Right? So if you set it up right, give it reasonable initial guesses, this should be able to converge and solve it. Right? So anytime you encounter a scenario when you're solving a complex problem and you're like, if I solve this, then I solve this, then I solve this, then I solve this, right? And you find yourself doing this like leapfrog, trying to get it to converge, what you found is that you have a system of nonlinear equations. So you can solve them simultaneously. Right? A lot of people will sort of resort back to this iterative kind of jumping back and forth. If you ever find yourself in that scenario, just think, hey, should I just solve these equations simultaneously? And computers are very good, so if you give them good initial guesses, they will find it in the blink of an eye. So that is number 4. So let's go to the process flow diagram just to reiterate this one. So what we're talking about here, oh, I remember this now. So it says 220. I'll double check what I have in my calculations. I don't remember if I'm right or if the process flow diagram is right. Probably the process flow diagram, but we can still keep it to 210. I'll double check this because there's an inconsistency here. I'm saying 210, this is saying 220. Let me check and give you clarification on which one I actually want. So here you're saying 0.3 of the feed to the methanol synthesis reactor, right? So this is after the recycle loop here, right? So this is after mixing with the recycle. In the real process, 30% of it enters at the top at some temperature, either 210 or 220, and then 70% of it, 0.7 of the feed here, is then coming in at different positions in the process. So I'm just asking you to balance this reactor a couple of different ways to see which may be the best design criteria. Because you'll notice that this reactor here doesn't have, this is an adiabatic process. So that makes it a little bit more simple because then you don't have to add in the additional complication of, running cooling water throughout the whole process, right? So not an easy unit to design. Okay, last question. Question 5. This is for how much money are we saving by doing energy integration, right? Is it worth our time to generate the steam? Are we saving $10 a year or $20 million a year, right? So how much does it cost to throw away certain amounts of energy? So question A is how much money can we save in millions of dollars a year, so obviously it's not $10 a year, by combusting the methanol synthesis reactor loop purge stream by offsetting some of the methane used, okay? So we're going to assume that the purge stream enters the burner at a temperature of 35 degrees C, but the air also enters at 300, just like in the burner for the steam reforming reaction. So what I'm saying in this part here is we're just going to take this gas that's at 35 degrees C that we're purging from the top of our flash drum, right? We need to purge because we need to remove any contaminants and inerts in the chemical process because they can accumulate. So we're saying, come on projector, there we go. Let's take this purge gas and then send it to the top up here and replace some of this natural gas. So the natural gas is coming in at 30, but the purge gas is 35, so use the 35. And it's going to be mixed with this air at 300 degrees C, right? So in this case here, the purge gas is going to have a very complex composition, but we know our combustion reactions. All of the hydrogen goes to H2O. All of the methane goes to carbon dioxide and hydrogen. So balance all of these products as if they were, reacting to form CO2 and water, right? So you'll have to do some material balance work in order to figure out what the composition of the combusted stream is, and you'll have to do that based on the 5% excess with the humid air as well. Does that make sense? So we're going to burn that instead of just throwing it away. Question?
Oh, so we're mixing the purge stream in with our airstream to the burner? Is that correct?
So what you're going to do is this purge gas stream here is going to have a certain composition of hydrogen, of methane, of carbon monoxide, of carbon dioxide. Okay? For every one H2, how many oxygens do you need? 1/2. For every CO2, how many oxygens do you need to burn it? 0. Carbon dioxide is the combustion product. That was a trick question.
Oh, I thought you said, okay.
For every carbon monoxide, how many oxygens do you need? 1/2. Okay. For every methane, how many oxygens do you need? I think it's 2. Right? So you'll need to figure out what your theoretical required oxygen is to burn this purge gas, add in the 5%, add in the humidity, because that's what you're actually going to be burning it in. Then those air streams are going to be entering the reactor at 300. Your purge gas is going to be entering at 35 degrees C. Then you'll be determining the outlet composition based on the steam reforming reactor's outlet condition, which is the 960 degrees Celsius. Right? So your purge gases are going to be leaving at these same conditions, and you're going to want to figure out how much Q heat is given off. And then I've got a conversion factor of about $3 million per BTU. Right? So you're going to have to scale this up from kilomoles per hour to the whole year to figure out how much money you are saving in millions of dollars a year by burning that effluent or the purge stream. Yes?
You can burn carbon monoxide?
Of course you can.
Whoa.
The goal is generally not to make carbon monoxide if you're burning stuff. It does happen. But one of the reasons why your catalytic converter is in your car is to eliminate any carbon monoxide that may form or unreacted hydrocarbons. So your catalytic converter is a platinum catalyst. That's why people like to steal them, because platinum is not cheap. So your catalytic converter is a platinum catalyst that is activated at high temperatures. So the worst time for emissions, when you start your car, your gases are cold, your catalytic converter is cold, so the catalyst doesn't work very efficiently. So when you start your car in the mornings and it's cold outside, you will be releasing a lot of organic compounds and uncombusted gasoline, potentially carbon monoxide and other hazardous material. But once your catalytic converter heats up and they get quite hot, like 1,000 degrees, then it's very efficient at finishing the combustion process. So it'll take all those COs, turn them into CO2s, take unreacted hydrocarbons, and combust them completely. So then it kind of heats itself up. Yes?
So essentially we're seeing how much energy we can get out of that purge stream and how much methane we can reduce in our feeding into the burner.
Correct.
Okay.
Yep.
So
Yes.
the natural gas feed, that has methane in it. The methane in that is used for both the burners and the reactor, right? Okay, so for, I guess the project part one is already even, but like, just for clarification, question one.
Yeah.
Project part one, that was supposed to be 1.6 in megapascals, right? Not 1
So all of the values I'm asking you for are independent of the pressure. So I'm asking you for flow rates in kilomoles or standard cubic meters.
Well, one of them. Wait, what is the standard?
A standard cubic meter is a flow rate measurement.
Doesn't that depend on pressure?
No. 22.4 cubic meters per kilomole.
Oh, okay.
So it's not ideal gas. Okay, last part is I'm asking the same thing, but instead, if you still use that conversion factor of, what is it, $3 per million BTU, how much money are you saving by generating the superheated steam? So when you're generating the superheated steam by cooling down the effluent from the methane combustion, and when you're cooling down the effluent from the steam reforming reaction, you're generating steam in two locations. How much heat are you extracting out of that? And what is its financial value if you use a conversion of $3 per million BTU? So they were asking you how much money are you saving by burning the purge gas stream and by generating that steam. So you'll start to see the scales of chemical engineering and why we care so much about this energy integration thing. All right, if you need more time on the project, let me know. Otherwise, enjoy your weekend.